Howdy, Calc 3 students. I'm going to try and do two Lagrange multiplier problems. Lagrange multiplier problems usually sound the same when they start out. You usually have some kind of surface, in this case xy plus 1, that is subject to a constraint, and in this case it's a x squared plus y squared minus 1. The constraint is a set of points that that are in the xy plane, and your surface is being limited to just those points, and you're trying to find the highest point on the surface above the constraint. So if you have x squared plus y squared minus 1 equals z, that's kind of a cylinder shape. But if you look at just x squared plus y squared minus 1, that's just a circle. It's a circle with radius 1. So here's what the problem actually looks like. You have a circle of radius 1, and you have this kind of saddle-y looking thing above it. In the quadrant where x and y are both positive, so that would be this quadrant there, the surface is high because it's xy plus 1. If you're in a quadrant where x and y are both negative, which is where my left thumb is, this part, the surface is again high. If you're in either of the other two quadrants, you're at a low, because now x and y are different signs, so you're subtracting when you do xy from 1. So you're looking for the highest points on that surface subject to this constraint, and Lagrange had the genius idea that the highest points happen when the gradient of f is equal to some constant times the gradient of g. Because if you remember, the gradient naturally points in the direction of greatest increase. So if you're trying to max this, surface, you'd like to get the gradient of this surface pointing in the same direction. In other words, being a constant multiple of that gradient. And remember, this is a vector equation. Grad f is a vector, so is grad g. Lambda, that's lowercase lambda. So if you can imagine being Joseph Louis Lagrange, who comes up with this method, your last name starts with L, so you can call this constant the Greek letter that goes with L, lambda, if you want to, because you're the first person to think of this idea. So we use lambda. It's just a constant. And in fact, we usually don't even solve for lambda. Usually we just use lambda as this guide. We use lambda as a guide. You'll see. All right, so let's do this equation. Let's do what it says. So what do we do? Well, I have special guest Harry Potter, who is doing the class with us, and Harry says, oh, he doesn't know what to do. Well, use the gradient operator, Harry. Use your gradient operator. So Harry's going to take the gradient operator of f, and that's going to be vector. The partial derivative of xy plus 1 with respect to x, which is a y. The partial of xy plus 1 with respect to y, which is an x. And that's supposed to be equal to lambda times the gradient of this. And that's going to be a 2x comma 2y. Pretty easy stuff. This is actually two equations. So one of the things is you equate the coordinates. Because for these two vectors to be multiples of each other, you have to have y equals lambda 2x, and you have to have x equals lambda 2y. Typical move is to solve for lambda. Because if you get lambda equals y over 2x, and you get lambda equals x over 2y, you can set these two equal to each other. And that says that y over 2x is equal to x over 2y. And you cross multiply, and you get 2y squared equals 2x squared, which implies not x equals y, x equals plus or minus y. And now another typical move, we're going up this way, another typical, is to use this constraint as written. So we have the x squared plus y squared equals 1. Now we're treating g of xy as if it's equal to 0. But the idea is the constraint is the unit circle. The minus 1 really doesn't matter. It's the x squared plus y that is guiding us. The constraint is the unit circle. So we have a formula for the unit circle. Anyway, so I have x squared plus y squared equals 1, and I already know x equals plus or minus y. So with x equals plus or minus y, and this constraint, these two ideas together imply that I have 2x squared equals 1, and that's x equals plus or minus the square root of 2 over 2, which on the unit circle is a pretty famous spot. That in this quadrant is here. And in this quadrant, with the plus and minus is not matching. So here's two pluses. Here's a plus and a minus. Here's a minus and a plus, and here's two minuses. If you remember, the surfaces are going to max above this point, and this point it's going to min below probably, but maybe still above that point and that point. So I know a lot about this problem already. I already know my answers. I'm going to have f max, f of square root of 2 over 2 square root of 2 over 2 is equal to f of negative square root of 2 comma negative square root of 2 over 2, and that's my max. And that's going to be, now if you remember, square root of 2 over 2 times square root of 2 over 2 is a half. So this is 3/2, and that's my max. If you do f of opposite signs, okay, so that's in one of the other two quadrants, you're going to get negative a half plus 1. So this becomes a 1/2, and that's the min. Now, what's very cool is we can check. We can check. We can do our own check. So if you remember, square root of 2 over 2 is approximately 0.707. Since square root of 2 over 2 is approximately 0.707, let x equal, how about just 0.7? Now, x squared plus y squared equals 1 implies that y, in this case, is equal to 0.714. So I did this calculation ahead of me, or I did this ahead of time. I did this ahead of you. So what I'm doing is I'm finding a point that's on this unit circle, but x is 0.7 and y is 0.714. So the y coordinate's a little above 0.707. The x coordinate is a little to the left of 0.707. But it's a point that's still on this circle. Now if I've done right, then f of 0.7 comma 0.714 is going to be less than 3/2. That's supposed to be my max. So I did this on my calculator because it's just xy plus 1, and my calculator gave me the very happy 1.4999. So I drew a little happy face on my scrap paper that I was preparing ahead of time for you guys. This, I'm happy because 1.5 is my max. When I went a little bit away from the point square root of 2 over 2 comma square root of 2 over 2, I went a little bit away from it on the unit circle, and I got a slightly lower z coordinate. That's a very good sign that this 3/2 is a max. So that's a typical Lagrange multiplier problem. Let's take it from the top. We had a surface subject to a constraint. We took the gradients and set them equal to each other with a constant multiple lambda. We didn't find a value for lambda, but we did solve for lambda in each equation and then just substituted. Since lambda is equal to these two things, we substituted, got this equation, cross-multiplied in this case, and we got x equals plus or minus y, which if you think about it, it kind of made sense. We're trying to max that surface, which if you remember what the shape was, that x equals y seems like a very reasonable thing to happen. X equals y in the unit circle means you're at those 45-degree markers. You were at square root of 2 over 2, comma square root of 2 over 2 in the first quadrant, etc. So my max is when x and y are the same sign. My min is going to be when x and y are opposite signs. So my max is 3/2. I get the min for free. I mean, we were asked to find the max, but we're also finding the min. Because the gradient, when it's pointing to the direction of the highest change, in the opposite direction, it's pointing to the fastest decrease. So we could be pointing at the fastest increase when we see the vector as something going up, but we could be pointing at fastest decrease if we see the vector pointing down. So the little check thing off to the side, a very wise person thing to do. But remember, the point that you check has to be on the constraint. You can't just check anything. You have to check a point that's on the constraint. All right, got another one to go. Let's do it. The other one that we have is a slightly easier problem. And it's f of xy is a plane this time. I chose the plane f of xy equals 3x plus 4y minus 7. So that's z equals 3x plus 4y minus 7. So it's just a plane that's tilted in all three directions. I said for my constraint, it's this ellipse. Let me show you the ellipse. My constraint is this ellipse. So in the x direction, it goes 4. In the y direction, it goes 3. So that's my constraint. So I have a plane that's tilted, and I have this constraint. Now the ellipse formula turns out to be x squared over 16 plus y squared over 9 equals 1. This is the thing we take the gradient of. All right, so we're going to do grad x equal, or grad f equals lambda grad g. Let's see if our man Harry Potter is capable of taking the gradient, because he's got the gradient operator. Harry, what do you think we're going to get from this? And Harry says, well, blimey, 3 comma 4 equals lambda times, now we got to do a little bit of math here. The 2 comes down, cancels with the 16, so I have x over 8. And the 2 comes down, and I get 2y over 9. I don't get to cancel the 2 that came down there. Now this gives me 2 equations. Let's write those 2 equations down. So I have 3 equals lambda times x over 8. Boy, I'm finding out some cool stuff here. And 4 equals lambda times 2y over 9. So if you solve for lambda, it's a typical move, solving for lambda. Lambda is equal to, just multiply by 8 and divide by x. So I'm getting a 24 over x. And lambda over here, I'm multiplying by 9 and dividing by 2y. So I get 18 divided by y. I did a lot in my head there. I hope I did it right. Now, that's lambda equals lambda, so let's take it over here. I have 24 over x equals 18 over y. Cross multiplication gives me 24y equals 18x. I can divide by 18 or I can divide by 24. I divided by the 24 because I'm just used to y equals. But you can do whatever you want. Y equals 18 over 24x. Cancel a 6 out of everybody, and I get a 3/4 x. This is golden information, because now what's the typical move? I have y equals 3/4 x, and I take it up to the constraint. If you remember the problem that we just did, that we outlined here, it was gradients, single gradient equations, relationship between x and y, substituted back into the constraint. That's the typical Lagrange multiplier dance. But when you go to do problems in the book, you're going to notice that some of them require a little bit of ingenuity sometimes. Sometimes you have to look and say, well, I'm going to do this. You know, you see some relationship that holds besides just solving for lambda, and you cash that in, saving yourself work. All right, but anyway, so this time we're going to boil it down to 24 over x is equal to 18 over y, which we had. Sorry, this thing here. The 24 over x equals 18 over y. Y equals 3/4 x. We're going to pop that in here. So I'm going to have the x squared over 16 plus the y squared is now 3/4 x squared, still over 9, then that equals 1. So this is good. It's an equation with one unknown. It's squared. So we might get 2 answers. Probably going to get 2 answers. But that kind of makes sense to me because we've got a plane oh, sorry, we've got an ellipse, and we have some kind of plane that's tilted above it. And there's going to be a max and a min. So Lagrange finds the biggest change, both up and down. So I'm going to be finding 2x coordinates out of this thing that are going to be useful. All right, so anyway, let's carefully work on this thing. X squared over 16 is fine. This is going to be 9 over 16 x squared, but don't forget it's divided by 9, which means I have x squared over 16 plus 9 over 16 x squared times 1 over 9. So that's kind of nice. Those 9's canceling. That doesn't have to happen, but it happened this time. And if you notice, I have x squared over 16 plus x squared over 16. So that's 2x squared over 16, otherwise known as x squared over 8, and that's equal to 1. So x squared equals 8, and that gives me x equals plus or minus 2 square root of 2. That's the square root of 8. So that's good news for me. That's not terrible. You might say, oh, God, that's not awful. And don't forget, we have y equals 3/4 x. So y is equal to plus or minus 3/4 of 2 square root of 2. So I can cancel out one of those 2's. So let's simplify my y real quick. That's plus or minus, canceling out one of those 2's gives me a 3/2 square root of 2 for the y. So now let's think about it. For this equation, for this plane to be maxed, I would want x and y to both be positive. To be minned, have x and y both be negative. So that's got to be it. Max f is going to be at the 2 square root of 2, comma, 3/2 square root of 2. And I did this calculation, and I did it on my calculator, and I got 10.0581. And then min f, which wasn't requested this time, but we're getting it for free. Min f is going to be when both of those are negative. So that's just an FYI. That's where the min will occur. Now, my check. I love doing a check. I love doing a check. That means I need an ordered pair that's on this ellipse and is kind of close to that point. Well, I did the decimal approximations, and I got a point 2.7 for the x, and for the y, I got 2.1345. This is a point that's on the ellipse. Now, if you look at where we are, the 2 square root of 2 and the 3/2 square root of 2, the 2 square root of 2 and the 3/2 square root of 2 is somewhere in here. So I've also picked a point somewhere in here to see if I get something higher or lower than 10.0581. So I did f of 2.7, 2.1345. So I did that work off to the side. And this came out to be, on my calculator, 9.638. A very nice thing. I get a smiley face because 10.0581 is bigger. So I went a little bit away from that point on the ellipse. I got another point on the ellipse, and I got a lower f value. That's evidence that that could be the max. That looks really good to me. There's been many times in my life where I'm doing a Lagrange multiplier, and I get to the check, and I get something that's bigger than my max, and then I go back through and I find I lost a 3 or something, and I fix it back up. So that's Lagrange multipliers, kids, 18.5 minutes. I'll see you on Wednesday.